So the first thing I wanted to sort of illustrate is that we use the same process for this for these assessments that we did for the Jamestown, but we chose new oostatic projections. And what we chose to use are these very recently published projections by Robert Kopp and others, just published in the fall of 2014, probabilistic 21st and 22nd century sea level projections at a global network of tide gauge sites. And the really nice thing about what they provided in this paper and the associated supplemental material is that they took what we are sort of accustomed to seeing in sea level rise projections, which are maybe a best estimate, maybe a standard deviation for uncertainty, and they made them fully probabilistic. So they built probability estimates for all the various components of global sea level rise and then combined them in a very rigorous manner to produce these full probability distributions for sea level rise. This will have some advantages that hopefully will become clear in the coming slides. Another nice thing that they provided is excellent supplemental material, which I'm going to describe. And then it also incorporates regional variability in the same way that the National Academy's report does. This idea of fingerprinting associated with the melting of large ice masses around the globe, which can actually change the gravitational dynamics and have regional influences on how sea level is expressed over, relatively small on sort of a regional spatial scale. And then ocean dynamics that might, wind patterns, for example, that might change the sort of local expression of global sea level rise. These were based, one interesting point is that these were based on the IPCC's projections, which means that there are some that would argue that these treat some factors like the melting of Antarctica, for example, too conservatively based on some of the available evidence. However, the argument that I'm going to make is that the sort of presenting the full probability distribution allows